Hello, everyone. I'm Julie Campbell, and I'm a postdoctoral researcher at the Ulster University in Coleraine. And I'm currently working on the catchment care project. And I'm looking at the challenges of recovery of good water status in lakes in the border regions of Northern Ireland and Ireland. And in particular, this study looks at Upper and Lower Loch Macnean. So the Arnie catchment is 3,440 square kilometres, and it covers parts of Fermanagh, Leitrim and Cavan. It has 4 Natura 2000 sites and some areas, special areas of conservation. And these are Quilca National Park, Ballyvoley Mountain, Ballintempo Forest to the north, and Corratrim limestone, which sits just below the N16 sign there. And then the Loch Macneans, upper and lower, sit in the middle of the catchment. So it's a fascinating and fun catchment. So you can see some images here. So we have Marble Arch Caves, which I'm sure many of you are familiar with. We have Claddagh Glen Park, which has some beautiful waterfalls. We have Gordatole Outdoor Activity Centre, which lies on Lower Loch Macnean. We have the Macnean Sculpture Trail. There we have this stone which sits on the shores of Upper Loch Macnean. We have Quilca Mountain, which is incorporated within the UNESCO World Geopark, which also includes the Marble Arch Caves. And we have some significant archaeological sites as well. This is a court tomb found near Belcoo, next to Upper and Lower Loch Macnean. So why are we focusing on these lakes? So you can see from the graph on the left that of the 21 lakes that lie within Northern Ireland, which are larger than 50 hectares in size, in 2015 and 2018, 5 of these had good water quality status. But in 2020, this number was reduced to 1. And we need to look and see why. And with the Macneans in particular, Upper Loch Macnean deteriorated from moderate to poor status, and Lower Loch Macnean deteriorated from poor status to bad. So we considered the land use within the catchment surrounding the lakes, and we looked to see if perhaps pressures from these land uses could be having an effect on the lakes. So the upper lake, which sits on sandstone and shale geology, has a mix of bog, forestry, wet woodland and rough grazing, with some small patches of intensive grassland to the north. Lower Macnean, which has limestone geology. This leads to better quality limestone soils. And so the lower lake is actually mostly surrounded by intensive grassland farming, which may be having an effect on the lake, as you can see later on. So let's have a closer look at the lakes, each of the lakes in particular. So this is Upper Loch Macnean. It has an area of 990 hectares with several deeper basins in it, the deepest of which is 24 meters, and the mean depth across the lake is 5 meters. It has 4 rivers which inflow into the lake. These are the Lurgan, the Eske, the Rue and the Black, as well as several small streams. But it only has 1 outflow, and this is the Belcoo River, which flows into Lower Loch Macnean. You can also see the long-term annual mean values for total phosphorus and chlorophyll listed in the table here, and also the residence time of the lake. This is how frequently the total water in the lake is flushed from the lake, or how long 1 molecule of water when entering the lake would remain there. So this is 0.3 years for this lake, which is just over 3 months or a quarter of a year. So this is Lower Macnean. So you can see from this image on the left that this lake is very different to the upper lake. It has an area just slightly less than half of the upper lake at 430 hectares, but it only has a mean depth of 1.2 meters, with a very small area in the middle of the lake, that dark dot, which you can see, which is 12 meters deep. It has two inflows, the Belcoo River, which flows directly from the upper lake, and the Drumharrif Burn, which flows from the north into the lake. And it outflows into the Arnie River at the southeast corner. You can also see again the total phosphorus and chlorophyll long-term annual mean values, slightly higher in this lake at 0.06 milligrams per liter total phosphorus, around the same for chlorophyll. But I especially want you to note the residence time in years in this lake at only 0.04 years. This is just over 2 weeks. So the total volume of water in this lake is flushed just over every 2 weeks throughout the year. So what could be the potential causes of the deterioration of these lakes? External nutrient loading from land management. These are diffuse inputs that come just from the catchment and run into the lake over the land from forestry, farming, and land clearing can have an impact. And then there are also point source or piped inputs, and these can be from wastewater treatment works, farmyards, septic tanks, and industry. Then we have internal nutrient loading. The external loads arrive in the lake, and these remain there in enriched sediments and accumulate over time. And these can be recycled back into the lake water column and cause eutrophication in the lakes, even when the external loads are quite low. There's also sediment resuspension in these lakes due to their large area and small depths. And this is especially true in the lower lake. So when storms happen, the sediment can be mixed into the water column, and any phosphorus or soluble phosphorus that's contained within the sediment can be re-released back into the water. So this is a diagram here of internal phosphorus loading. So the inputs come in, they're in the lake water, either in a particulate or soluble form. They accumulate within the sediment, recycle back into the water column, and then are flushed out in the P outflow eventually over time. So if we want to look at internal loading in the lake, we need to take a closer look at the sediment. So this we did by taking 2 cores from each of the lake using a mini Macroth core. The diagram of the core is here on the left. So you can see we've got the core tubes, which are 1 meter long, which are used to take the sediment. And then we have the core itself. The black tube is a pneumatic ram, which pushes the core tube into the lake. And then we have an oxygen tank, which is used to push that ram down. And it's connected to the pneumatic ram with an air line and then a rope to lower and lift it all into the water. So we're just going to look at a short video here of how that's actually done. So you can see the AFB team dropping the core into the lake. And then it just sinks down. It's connected at the top. You can see the airline and the rope as it's lowered down. So they're just going to lower the core until it reaches the top of the sediment in the lake, taking care not to snag the airline. That's it, lowering it down. And they can feel whenever the core actually reaches the top of the sediment. And once that happens, it should be anytime soon, just there. James is going to turn on the airline, push the pneumatic ram with the core tube into the sediment. Okay, so once that's done, they'll see bubbles on the lake surface, and that shows that the ram has fully deployed. And now they're going to pull the core back up again. And hopefully they'll have got a lovely sample of core coming to the surface now. It's going to be heavy if it's got a core on it. Yvonne's just going to put the bung in and see the sediment just to stop it from running out. So we take these cores to the lab and we put it up on this assembly here, and we slice the core into 1 centimeter slices. A subsample of each slice is then sent to University College London, where it's analyzed using radioactive isotopes and dated. And this dating analysis also gives us the sedimentation rate of each slice and for each year of the lake. So if you look at the graph on the left, you can see that at 40 centimeters deep within this core, as we sliced it down, the sediment was actually laid down in 1900. And the radioactive isotopes also allow us to sort of pick up on key events which have happened throughout the world. And we can pick up on a spike in cesium-137 for Chernobyl, the Chernobyl event in 1986. And that actually lies at 12.5 centimeters deep within the sediment core. And it's actually used as a dating tool for analysis for lakes in Ireland. So let's say we stop all the external loads. So we stop all the inputs coming in, and we've only got the phosphorus that's contained within the sediment. How long would it take for that to be reduced and for the lake to fully recover? That depends on 4 key issues within the lake, or 4 key variables. We have the hydraulic residence time, which we've already discussed, which is the length of time that the lake is, or the water stays in the lake, or how frequently the lake is flushed. We've got the sedimentation rate, which we get from the dating analysis, which has come back from University College. And then we also need to look at how much phosphorus is in the lake, and whether that, or how much phosphorus is in the sediment, and whether that phosphorus is actually available to be recycled into the water column, or whether it's permanently fixed within the sediment. And then we have to look at the depth of the active layer. The active layer, as you can see in the diagram, is the layer which will continue to recycle phosphorus back into the water column. And once you go below that active layer, the phosphorus is actually permanently fixed within the sediment, and there's no more recycling. So we need to know how deep down in the sediment we will need to go before the phosphorus becomes completely inactive and no longer impacts on the water quality of the lake. So we also do a chemical analysis on each slice of the sediment. So you can see in the left-hand diagram, this is the total phosphorus contained in each slice of the same core that you saw for the dating analysis. Total phosphorus is made up of available phosphorus and fixed phosphorus. We refer to these as labile and refractory. So the depth of the active layer is actually calculated whenever the available phosphorus in the core tube, or in the core, becomes no longer available for recycling. So the active layer, you can see on the diagram in the middle, whenever that left-hand line, which is the available or labile phosphorus, reaches 0, that's the depth of the active layer. So below that depth, no more phosphorus will recycle into the lake water column. Whenever we find out this figure, we are also then able to calculate what the available phosphorus would have been in the sediment whenever it was first deposited. So we take the relationship between the phosphorus, the available phosphorus as it is now, and the available phosphorus, or the labile phosphorus, as it was when it was fresh. And we look at the relationship between those two over time. So how does it change as the core ages, or as we go further down the core tube? I know this is quite mathematical, but I'll try and explain it as simply as possible. So y equals mx plus c is the equation for any straight line, and m is the slope of the line. But M also shows the relationship between the two available phosphorus fractions and time. And that actually gives us the rate of change in the available phosphorus over time or during the years as it moves down the core. In this instance, M is equal to 0.103. So we know the sedimentation rate, we know the depth of the active layer, we know the relationship between the phosphorus when it was fresh and the phosphorus, the available phosphorus now. And we also know the hydraulic residence time or the flushing rate of the lakes. So using all of these variables and a mathematical model, we can calculate how long it will take for the available phosphorus in the sediment to decrease by these percentages. So a 50%, 75%, and a 90% reduction. If we look at Upper Loch Macnean with just over 3 months of residency time, we can see that in just under, look at the far right-hand column, 90% reduction, we can see that in just under 10 years, there'll be a 90% reduction in the available phosphorus in the sediment. So in just under 10 years, if there are no further external loads to the lake, the internal load within the lake will have been depleted by 90% and the lake status should fully recover. But in the lower lake, because the residency time or the flushing time is so quick in that it's only 2 years, we can actually achieve this 90% reduction in less than a year. In fact, 0.6 of a year for a 90% reduction. But what about sediment mixing or resuspension during storms? What impact will that have on the lake? So you can see how, again, that works. So we've got our inputs coming in, but then we've got a windy day and we've got wind moving over the surface of the lake. And as that wind speed increases, the depth of the mixed layer, or the depth of the wave mix layer, as the waves get bigger and bigger and bigger, once that wave mix layer actually reaches the top of the sediment will start to mix into the water column. And any P that's, any available P that's within that sediment can then be sort of released into the water column and can affect the water column before it's flushed out in the outflow or the sediment resettles back down again. So how often would this happen? How often do these storms cause this sediment resuspension and potential release of phosphorus in these lakes? So what we did was we deployed a Technicap sediment trap. This is a 1 meter long trap with a 25 centimeter. Sorry, can I do that again? Shane?
Yeah, you're okay. Go ahead.
I only have 2 more slides, yeah?
Okay.
Okay, thank you. Can I just start again?
You can, yeah.
Okay. To do this, we deployed a Technicap sediment trap into each lake on 2 separate occasions. This is a 1 meter long tube with a 25 centimeter funnel at the top and a carousel of 12 bottles at the bottom. Each bottle is open for a period of time, and then given wind data for that period of time, we can then plot the weight of sediment collected against the wind speed. And you can see that for the storm in Lower Loch Macnean on August the 18th to the 24th, in this instance, each bottle was opened for 9 hours. So if you look at the graph, the blue bars are the amount of sediment collected in each bottle, and the orange line is the wind speed. So you can see that when the wind speed was at its highest, most sediment was collected in the bottles. So then we plotted that again. So for that storm, and we plotted the actual wind speed against the amount of sediment. And you can see this R squared figure is equal to 0.645. That means that 64% of the change in the amount of sediment collected is related to an increase in wind speed. When we looked at the wind data in more depth, We saw that storms only cause significant mixing whenever the wind speed exceeded 15 knots per hour, which is about 18 miles per hour. And these events only occurred at 1% of the year. So because the lakes are so frequently flushed, these events will have little or no effect on overall water quality. So in conclusion, internal loads from the sediment is not responsible for the deterioration of lake water quality in these lakes. So external loads need to be the focus of lake improvement measures. Upper Loch Macnean has pressures from septic tanks in poorly drained, boggy areas, forestry and agriculture. And Lower Loch Macnean is impacted by the Drumharroch burn, intensive agriculture, and inputs from 2 wastewater treatment works in Blackline and Belcoo. These external loads, therefore, must be assessed and addressed before any long-term improvement in lake water quality can occur. Thank you very much.